let's see. Last time we talked about sort of like deterministic optimal control algorithms. Let's say kind of summary. And then we did kind of, yeah, like in particular, right, we talked about sort of LQR versus MPC, and then like sort of DDP or indirect methods versus Dirkall. And then we did this kind of Quaternion crash course intro. Any questions about any of that stuff? Yeah, cool. Okay, so today we're basically going to double down on our Quaternion conversation. We'll do a little recap, and then we're going to dig into optimization with Quaternions. If you want to be fancy, this is like optimization on Lie groups, blah, blah, blah. Optimization on, technically, this is optimization on SU2. Anyone's into that. Yeah. Special unitary grouping, which is what Quaternions are. That's the double cover of SO3. The SO3's rotations, right? We said the Quaternions are this weird like double cover thing. They're two Quaternions for every rotation. So they're actually a different group. They're a group called SU2. That's the unit Quaternion. That's what it's short for. Fun fact, I don't know. But it's, yeah, that's what we're doing. As an aside, you don't need to know this. It's sort of random extra information for fun. Okay, cool. Shall we? All right. So I feel like I should say something about this now. Yeah, SU2 are 2x2 complex matrices, and it turns out they're Quaternions. Okay, cool. So just like a quick recap from last time, and we're going to kind of dig into this stuff a bit more and hopefully try to give you some geometric insight today. Think of these guys as 4D unit vectors. And they have a multiplication rule that basically acts like matrix multiplication. So anytime you're wondering what to do with these things, like just think about them as rotation matrices. If I want to like, combine two in, some order, think about them as if they were matrices, and that's kind of works out. So we got, and we're going to use the asterisk or star or whatever for this in here. And this looks like some weird generalization of like dot and cross products. So I've got like scalar and vector parts. And in terms of those guys, this product looks like this. And it includes both the, classic dot and cross products in it. And I mentioned as an aside last time that this was actually invented first and it freaked people out. So Gibbs, kind of split this apart and like invented dot and cross products. And then we talked about how we can rewrite this thing as a couple of different matrices. So we can write down the left multiply matrix, which is this guy. And this gives sort of think about this as, the left Jacobian of that matrix of that quaternion multiply. And there's a right version as well. And the whole idea here is just so we can kind of write this guy out as L of Q1 times Q2 or R of Q2 times Q1. The reason being, this is the Jacobian. If I want to take the derivative of an expression like this, now I have a way of computing that Jacobian matrix, which we're going to use today to start doing optimization stuff with these guys. Okay, so that's multiplication. Then we talk about this conjugate idea that is the equivalent of the transpose for rotation matrix. It gives you the opposite rotation. So it's this rotation about the same axis, but the opposite direction. Yeah. Oh yeah, that's that skew symmetric cross product matrix. So V1 at times V2 or whatever equals V1 cross V2. It's a 3x3 skew symmetric matrix that's like literally just if I write down V1 cross V2 in components, and pull out the V1 stuff into a matrix, so that such that this matrix times V2 gives me V1 cross V2. That's what it is. That's how you figure it out. That is the definition. It's the cross product matrix. So it's in the notes from last time. I don't know. Go check it out. That's it. It's shows up all over the place. People call it different things. In like, I think it's fairly standard in like group theory context to call it the hat map or the hat matrix. I kind of like that definition because then you can also similarly cleanly define the unhat. Goes the other way, which is take the matrix and turn it back into a 3-vector, which is kind of nice. So hat and unhat, kind of, there's a nice sort of symmetry there. The other ways of writing it, I think, are just, well, a lot of people will write it as like brackets with a little cross product superscript or something, which I think is less clean. I don't know. That's how we're going to write it. It shows up in a lot of places. Thought of another way, that is the Jacobian matrix of the cross product. If I need to take a derivative of like V1 cross V2, that's how I get that Jacobian. So most of this stuff where I make up these weird matrices, the whole reason is taking Jacobians. Okay, cool. So this conjugate thing is, I read it like this, and we talked about last time. I want the direction, I want to just flip the direction of the rotation around. And if you look at the original definition of, the quaternion in terms of the axis angle vector, the top's a cosine and the bottom's a sine. So I flip theta, nothing happens to the top because cosine is symmetric, but it flips the sign on the bottom. So that's the definition. And then last time we made up this matrix called T for transpose. That's just got a 1 and then a minus I down here so that T times Q gives you Q conjugate. Again, we're just making up matrices all over the place here so that we can take derivatives, so that I know how to, get the Jacobian of these things. And then similarly, we have an identity quaternion, which corresponds to a rotation of 0, which if I plug it into the definition with the cos and the sine, it's just, and I guess I'll write this Q sub I or something like that. It's just 1, 0. Okay, cool. Let's see. This is, I'll review stuff. That hat map with, there's also a sort of hat map for quaternions. Remember, the hat map gives us the cross product. If I remember the definition of this guy, if I just wanted a cross product and I wanted to like stuff it in this quaternion multiplication, what would I do? If I just want V1 cross V2, how can I get that out of this guy? Well, so literally, all this goes. See that? So similarly, I'm going to define this sort of hat map for quaternions that acts the same way, which is why I'm calling it that. So if I have some, omega, we're gonna make it. It's just a quaternion with 0 scalar part and like just the vector part. We're gonna similarly make up a matrix for that called H, such that it's such that H times omega gives us that, which is just a 0 and then an identity block. And again, that's all this stuff is just so we can take derivatives. Yeah. Yeah. What we're going to do in practice here is for all the quaternion stuff, we're going to do everything. So I'm going to make sure that it's clear when we do it. The goal here is to like define a bunch of matrices so that I can just live in matrix vector land. I learned this all the hard way. Like having weird notation for quaternion products and stuff, it messes you up as soon as you start like wanting to do mix and match vectors and quaternions and matrices. So the way, in my experience, the right way to do this is to basically always basically always use matrix vector notation. So kind of what I'm doing right now is setting us up so that we can like have all the matrix vector stuff we need to like always write this down in matrix vector notation. Then you know how to code it up and it's super clear and you don't have any weird mix and match stuff. To be super clear, I made all this notation up. Like all the matrix notation that's in here because we were doing a lot of this stuff and like mixing and matching like matrices and stuff, and it gets super confusing and super buggy and messy. And it's just way cleaner to like double down on matrix vector stuff and live there all the time. Yeah. Yes. So this is another very, very annoying thing. We mentioned there's conventions for like body to world, world to body. and this is annoying, and there's also mixed conventions on how you stack the quaternion. This convention in robotics is S on top, B on the bottom. The convention in a lot of older aerospace literature is the opposite. And there's also really frustratingly, there's a convention that writes the rotation matrix as body to world, but the quaternion world to body in a lot of old aerospace papers. It is infuriating. So there's like, roughly speaking, a half dozen different conventions for all of this stuff floating around in the literature, and you can never trust anything you read in a paper. So if you're going to read a paper that has anything with rotations in it, like any quaternion stuff, basically go read it, but then like rederive all of the specific details yourself. You cannot trust anything. I'm sorry to tell you. Yeah, life is hard. This is very annoying. There's like 50 years worth of conflicting stuff from multiple fields. Roughly speaking, aerospace, robotics, and physics all do different things, and mix and match in frustrating ways. So you can't basically code up anything out of a paper. You need to like go run down the math yourself. And I would suggest, having done this and experienced much pain, I'm trying to show you like a coherent, consistent way to write it down and like do it all such that you don't sort of have these issues. So I highly recommend stick with these conventions. I'm basically showing you, like, roughly speaking, the robotics conventions that are fairly consistent. And then also this sort of matrix vector way of writing everything, which I highly recommend sticking with, because it just makes code, it makes it clean to write it in like MATLAB, Python, whatever. And it avoids a lot of weird issues. End of rant. Sorry. It's super frustrating. There's a lot of terrible stuff out there. All right, cool. So let's see. I think that's all we need. Okay, so that's recap from last time. Now what I want to do is sort of try to give you some geometric insight into like what's going on here a little bit, and like in particular to try to get us towards what we need to like compute gradients and start doing optimization on these things. So the first thing I want to talk about is a little bit of geometry. So like, I already kind of said this at the beginning of class, but it should be somewhat obvious to us, right, that these things are unit vectors in R4, and so therefore the set of all quaternions is a sphere in R4, though. This is called the three sphere, and the reason is that it's the surface of the sphere is three-dimensional, right? So it's embedded in R4, but it has 3 degrees of freedom on the surface, just like the classic sphere that we know, like the globe. That's actually called the two-sphere, and that's because there's 2 degrees of freedom on the surface of the sphere. Okay, so let's say I've got the sphere, I have this quaternion over here, Q. So let's write that down. Q lives on a sphere in R4. How about Q dot? Where does Q dot live? So if I have this quaternion, I'm moving around, right? My body, rigid body's tumbling, whatever. If I'm thinking about the derivative of Q dot, what space does that live in? Well, in this picture, where does it live? Yeah, exactly. It lives in the tangent plane to this sphere, right? That's exactly right. So let's draw a little cartoon of that. So like this kind of guy, right? That's what Q dot looks like. And it lives in, if I imagine like drawing a little tangent plane, kind of centered here, that's where it lives, right? So yes, it is three-dimensional, but if I were to draw it in here, like at any given point, it lives in this 3D tangent plane, right? That makes it, no, you're not wrong. Like it is a three-dimensional, it has 3 degrees of freedom, right? But yeah, in spirit, that is absolutely right. It is a three-dimensional thing, right? It only has 3 DOF, right? Okay, cool. So yeah, that is the right color. Q dot lives in the tangent plane at Q. Okay, so that's clear to everybody. We've got this weird sphere situation. At any given Q, there's some tangent plane, and that's where the derivative lives. Okay, cool. So I think where we're headed with this is that derivatives are, like, while the Q itself might be, 4D in some sense, or similarly, the rotation matrix is this weird higher dimensional thing. The derivatives are always sort of in this 3D tangent space, right? Okay, so that's important. So let's now think about like kinematics a little bit. We wrote this down last time, so now hopefully going to give you a little bit more geometric insight into what's going on. So we know that q dot is this like tangent plane situation. There's 3 dots, but if I'm just going to write q dot down as a vector, that is a 4 vector, right? So it lives in R4 somehow. But then like we all know that the angular velocity, the omega, which is kind of the time derivative here, is 3D, the 3 vector. It's what you measure on your gyro. So like, how do we reconcile these things? This is kind of funky. So last time we wrote down this kinematic equation that I didn't really derive in any detail, and we're going to kind of circle back and try to derive that a little bit now. So we have this guy, q dot is this thing, like q times omega hat sort of thing, and it's specifically, this in our matrix notation, which we're going to try to stick with. Cool. Okay, so here's like how you get there from this q dot picture. So if I've got my like sphere situation, I've got my q over here, say. Let's say my q dot is this guy. So if I look at this kinematic equation, let's think about this for a second. By the way, that equation looks roughly the same for the rotation matrix case, right? We did that too. It's the same deal. So what this is actually doing is q dot is what this is doing. Actually, we're defining omega. It's kind of clear. So what that's doing, like if you want to think about it geometrically a little bit, is it's actually saying, I'm going to choose to define, so omega is defined in the body frame, right? It's my gyro that's bolted to my, robot or whatever. And so I'm actually going to, like, the geometric picture is that omega is always defined. It's always defined in the body frame. And in this context, because this guy is like the body to inertial rotation, that corresponds to being defined at the identity quaternion, which roughly speaking here, I would think about as defined at the North Pole. Which I don't know, based on the stacking of that thing, it can be weird, but think about it like I think about it as the North Pole, also because I came up in aerospace where we wrote it the other way. Whatever, not that important, but I think you can kind of intuit this as North Pole. And then what's going on here? So omega is always defined in this one particular tangent plane, say at the North Pole. And then what this kinematic equation is doing is rotating it from the North Pole down to our current q. That makes sense? So I'm taking this North Pole vector, and this guy is hitting it with q to rotate it down to the current tangent plane where q is. And then the current q. Does that make sense, everybody? Yeah. Yeah, that is a good question that is not yet obviously clear. It's coming from the definition in terms of the axis angle that we originally wrote down, where it was like cos theta over 2, sine theta over 2. Coming from there, that's like an algebraic answer. There's also a geometric answer that's a little weird and subtle that maybe we'll get to in a little bit. So bear with me. But this is the kind of the geometric picture, I guess, at least for where this is coming from. Let me move this over here and like write this down. So omega is always written, let's say, in the tangent plane at the identity. Then the kinematics equation up here rotates it to the tangent plane at q. So it can be like added on to that q, if that makes any sense. That's sort of, I don't know, some intuition for what's going on there. And I want to like give a little bit more intuition for this stuff by digging in on it. So all this weird quaternion stuff is actually like the 3D generalization of complex numbers in the plane. If anyone's seen like complex phasors, you can kind of think of these as like rotations in R2. So I want to kind of write that down real quick and hopefully give you some flavor. Um, for where this is coming from this way. So hopefully everyone's seen like, I don't know, took some like circuits or EE stuff and saw this kind of picture. So we've got like, I don't know, we'll write as XY here. And then let's say we've got some vector V, some theta here. This guy I can write as cos theta plus I sine theta. This guy's a unit vector. I can think of these as real and imaginary components for a complex number, or X and Y components, right? And then I have in this case, right, if I stacked these guys, I'd get like, cos theta, sine theta, and then from there, V transpose V equals 1. So this is complex plane, right? I've seen this before. So now what I want to do is write down dot. Okay. So if I just chain rule this guy, this is partial V partial theta times theta dot. Yeah. So if I write down partial V partial theta, I'm just going to dip that expression right there. That's my kinematic Jacobian. That's minus sine theta cos theta times theta dot. Cool. And like if I were to, I can also kind of think about this another way. I can slightly expand this as if I write my theta dot down there not as a scalar, but again as a 2D vector. And then this is kind of the standard 2D rotation matrix. And now it should be hopefully pretty clear like what the picture is doing. So this is rotation matrix, obviously. And this is the like complex number equivalent of that hat map, where I take things and throw it in the vector part, which is the imaginary part here. And so then if I draw the picture, this is my kinematic equation now for like this complex phasor situation, analogous to that quaternion situation. So I've got like my V over here. This is theta. No, I don't want to do that. Okay, V theta. Theta dot is defined as like the unit in the unit y direction. So that's writing it at the identity, which is 0, 1 over here. So this is my, this is theta dot. And then if I imagine like my, then this is V dot over here. And what's going on is, this guy is like where my current vector is. Okay. Hopefully that made some sense or clarified the situation somewhat. Let's see. So this kinematics kind of equation up here rotates theta dot from the tangent plane, which here is like the tangent line, at the identity, which is theta equals 0, to tangent at the current V. Cool. That makes sense. So it's like this picture generalized to 3D, right? So hopefully that gives you a little like geometric insight as well. Any questions about this stuff so far? Okay. Now we're going to talk about differentiating quaternions and like doing some okay, so there's kind of two key things to keep in your head while we do this. The first one is that the derivatives of like rotations, even if our like base representation is not 3D, like it's a quaternion or a rotation matrix, the derivatives live in this like tangent space, and the derivatives are really 3D. They're really like this kind of idea of a 3D tangent vector, or a 3D vector living in this particular like tangent space. So we want to write them that way. Derivatives are really 3D tangent vectors. And then the second big idea. So first one is derivatives are always 3D, even if the rotation representation is not. And then the second one is that rotations compose by multiplication, not addition. Like the key idea here is rotations are not vectors. They're a weirder, different thing, like matrices, quaternions, whatever you like. They do not add, right? So, and in particular, the reason they do not add is just the physical reason that they don't commute. So if I do like 90-degree pitch, 90-degree roll, and up here, if I flip the order and do 90-degree, 90-degree pitch, I'm over here. So that like non-commutative nature, that is reflected in matrix multiplication, right? If I flip the order of two matrices, I get different answer. It's not reflected in vector addition. Like if I flip the order of addition, I get the same answer, right? So it can't be addition. It has to be something else. And in particular, the math that captures that fact is multiplication, right? So compose by multiplication, not addition. Okay. So we agree on those things. So now we're going to talk about, to like get us into like derivative land, is start talking about like infinitesimal rotations, really tiny rotations, and start looking at what that does for us. And so let's think about that like a little tiny quaternion, a rotation that corresponds to a tiny rotation. It's still a unit quaternion, right? It's a small angle unit quaternion. So let's write that as like delta Q. And if I remember my definition of, in terms of, axis and angle over here, this is what we had from last time. And what I'm going to do now is just plug in a tiny theta. So if I have a tiny theta, kind of doesn't matter what the axis is, what happens to the cosine in like a small angle situation? One, what happens to the sine? It's approximately theta. And in this case, it's a 2 in there, so it's a 1/2. So the bottom of this turns into 1/2 a theta. And remember what we called a times theta before? That's our axis angle. So this thing's approximately a 1 on top, which remember 1, 0 is the identity. So really what this is saying is it's in the identity plus like half of the axis angle sort of down here in the vector part. That's how I'm going to write that. And this guy's a small axis angle vector. Okay, cool. So this is how we're going to kind of bootstrap our small angle stuff. So let's keep chugging here. So this is equal to, I just said, like an identity quaternion plus 1/2 times like the axis angle put in the vector part, which is our hat map. So this is identity quaternion plus 1/2 HB based on our like definitions. Cool. Okay, so the next thing we're going to do is uh, look at a small perturbation. Yeah. So, I mean, as far as this is going, like, I mean, really right here, it's just like a definition of like, I take the vector and I shove it in the vector part with like no scalar part. Algebraically, it's also the same thing as the cross product matrix for, so in quaternion land, it means take the vector and make a zero scalar part quaternion. In rotation matrix land, it means the two symmetric cross product matrix. They do the same stuff. There is a like deeper thing there, which I feel like is maybe a long digression into some group theory stuff. If you care, we can talk about this later. If you care and you want to like go look up some stuff, the hat map thing, these are elements of the Lie algebra, and the Lie group or the unit quaternions or the rotations. The rotation equals Lie group, this like hat mappy stuff, and these like 3D vector things. These are the Lie algebra. And yeah, if you want to Google that, cool. We can talk about it later. I can like punch you some stuff. It's probably too much of a tangent for right now, but I'm happy to nerd out about it. Okay, so let's try now composing like this little rotation with a finite rotation Q. Let's see what happens. So if I have some, the idea here is I want to compute some perturbed Q prime, which is going to be Q times a delta Q. So using our notation, and I should write it like that, I guess, this is L of Q. And then remember times this guy, like identity plus 1/2 H E. We just figured out. And if I now kind of like just distribute that out, it's Q plus, that's the identity term, plus 1/2 L of Q H B. Cool. So this is like, again, if I were to take a tiny infinitesimal rotation and perturb some, other, some arbitrary quaternion by it. The reminder is if I perturb, if this were normal vector x and I were perturbing it by a little delta x, it would just be x plus delta x, right? The idea here is the only difference between this and vectors now, as far as like these small perturbations, aka like derivatives. So instead of q plus delta q, remember they don't have to multiply, we got q plus q over delta. So effectively, the price you pay here is you pick up an extra Jacobian when you're like trying to represent perturbations. So instead of x plus tiny delta x, it's q plus tiny little phi. And this Jacobian thing shows up a lot. And we're going to give it its own name. We're going to call this G of Q. And to be clear, this guy's 4 by 3. And it's mapping our little 3D tangent plane perturbation into a 4D thing, like tacked onto my quaternion. And we're going to call this guy the attitude Jacobian. Okay. A quick note on this. We derived all of this, like, with this quaternion picture and like whatever. And we weren't super explicit about what the parameter guy is. Like, is that a, axis angle? Is that a vector part of a quaternion? Is it something else? I guess we kind of said it was a small axis angle. It turns out for tiny rotations, for like infinitesimal rotations, it doesn't matter. It turns out that all 3 parameter attitudes, so whether it's Euler angles, axis angle, vector part of your quaternion, if you like, Gibbs vectors, Rodriguez parameters, whatever, there's a bunch of these things. Turns out for small, like infinitesimal, small angle stuff, they all linearize the same way. And so this attitude Jacobian, turns out it doesn't matter which parameterization you use to derive it, it comes out the same at the end of the day, which is kind of interesting. Yeah, so that would, like, you pick up a permutation, and literally that just corresponds to flipping the ordering of. So yeah, then it would be, so I guess up to a permutation, if you want to be weird and flip your axes around, that literally corresponds to like, so usually we define roll pitch yaw as rotations about the XYZ axis. So under tiny rotations, that corresponds to like an axis angle with XYZ component. Makes sense? So they're under infinitesimal small magnitude, whatever, if you define the things the same way in terms of the coordinate axes, it carries over. If you want to be weird and order your Euler angles a weird arbitrary way, fine. Then you just need a permutation matrix that flips the ordering of the vector. Does that make sense? So yeah, like roll pitch yaw usually is roll about x, pitch about y, and then yaw about z. And so that for very, very small rotations, that axis angle vector with xyz components is the same thing. Okay, that was a little weird aside. Hopefully that made some sense. So I'm going to just write that down real quick. Note, we can use any free parameter rotation representation we want to for phi in this stuff. It turns out, yeah, they all linearize the same way, which is kind of interesting. And there's like some deeper thing going on there, right? There's like a deeper kind of group theory thing happening there. But in principle, you can use any one you want when we're doing this stuff, and that attitude Jacobian doesn't really change, at least not up to some weird permutation or scaling. I guess, yeah, like you could also decide to use not radians or something weird, right? And then it would have a scalar that you would have to impedance match, but linear is the same, like up to caveat, up to a permutation / scaling. Okay, good point. Okay, so yeah, basically just to illustrate that, like the axis angle looks like this, right? It'd be like cos norm phi over 2, and then over here, get the axis, you do phi over norm phi, and then similarly sine norm phi over 2. You could also do the vector part of the quaternion. So I could just like take the vector part out and use that as my representation, in which case, the bottom of the quaternion is just the phi. And then to get the top, I just compute square root of 1 minus phi transpose phi. It's just whatever it needs to be to normalize this guy. That's perfectly valid. I'm just showing you how to like reconstruct Q from any one of these 3 parameter things. The other one that's really common is called the Gibbs vector or the Rodriguez parameters. Has anyone heard of this before? Yes. So the way you write that down is, or the mapping back from that one is this. There's like a normalization out front, and then it's just this guy. It's almost like using front quaternion. So it's just showing you, actually, if I stare at this for a second, if I linearize all of these, they all give you the same attitude. It's like any one of these you want to use, like it doesn't matter. If you wanted to be sadistic and use Euler angles for this, same story. You'll get some bizarro mapping in here with like a bunch of trig functions. But if you linearize it for small angles, you'll get attitude Jacobian. Like roughly speaking, right? All the they're all higher order, and so under linearization, like you throw out all the higher order terms, you just get this at the end, which is clear in theory. Cool. Okay, so let's see what this is. Axis angle, which we already talked about. This is vector part of Q. And then this one is the Gibbs vector / Rodriguez. Yeah, I always get that messed up. That's a French Rodriguez. It ends with an S instead of a Z. Okay. Cool. So yeah, for us, just for like consistency or whatever, we're going to use the vector part of Q. It's easy and like less work. It doesn't really matter. But these Gibbs vectors also have some nice things about them and stuff. Okay, cool. So now that we did all this, there's sort of a meta message here, which is like the strategy for doing calculus with these things is literally to just take the derivative as if you were a normal vector, get your Jacobian, and then slap a G on it, slap an attitude Jacobian on it, and that maps it from whatever weirdo 4D quaternion derivative it would have been is a 3D derivative with respect to this axis angle guy that's nice and works the way you expect. So I will say it again. Take the derivative as if Q were a regular 4D vector, get your Jacobian or whatever for your gradient, and then everywhere there would be a quaternion, just slap an attitude Jacobian on it, and then everything works. Chain rule works, all the usual stuff works. So I'm going to write that out like with a few examples right now, just to kind of illustrate it. Okay, this whole thing lets us differentiate with respect to quaternions by inserting this attitude Jacobian guy in the right places. And I will make that very explicit right now, what that means. So with a bunch of examples, literally just anywhere there's a quaternion, you put an attitude Jacobian. And you can think of this as like impedance matching you from quaternion land back into like 3D tangent space land, which is where we want to live. Okay, so let's take an f of q. Let's think about like a cost function now. So if we have f of q, which is a function that eats a quaternion and spits out a scalar. So think cost function. So this guy we're gonna say is from, so H is the like blackboard bold is quaternion. It's from Hamilton, I guess, who invented them. So this is a function from unit quaternion to R. So like, let me just note that. This is short for Hamilton. Okay, so this kind of thing, which is, to be clear, gradient of a scalar valued function. The quaternion argument. I have del f, and we're going to kind of use this, like, I'm going to kind of slightly abuse notation where if I write that, I mean the like same impedance matched 3D gradient. Whereas if I write the partial f partial q notation, I mean the like 4D derivative. So this is going to be EF dq. So the other way to think about this is that attitude Jacobian is basically dq dphi, evaluated at q, like it's just chain ruling is another way to think about it. But there's like there's a rich geometric picture there. So this guy is just partial f partial q times g of q. Okay, so if it's a function that goes from a quaternion to a scalar, I take the regular Jacobian, we're just slap on the right hand side. Now, this guy, let's multiply my axis angle over here, a little p, and then get the thing out on the other side, the delta, scalar on the other side that I expect. Okay, so that's if it's a cost function-y thing, like a scalar valued function. Now we're going to talk about is, let's say we've got an f of q that maps us from quaternion input to quaternion output. And the scenario here is a dynamics function. So I've got like a rigid body dynamics where it's, like my discrete time dynamics where I have qk coming in and qk plus 1 going out, right? So it's mapping from a quaternion to a quaternion. So this is a Jacobian now. Right, and the recipe here is, what I want is, I want to put in a little phi on the right, a little infinitesimal perturbation, and I want to get out a phi prime, like an infinitesimal rotation perturbation thing on the output as well. So I need to put g's on both sides of this guy, right? So the idea is everywhere with the quaternion, I put a g. So if I got a quaternion on the input, I put a g on the right. If I got a quaternion on the output, I put a g on the left. And so that's kind of what's going on here. So I got phi prime equals, and I've got, keep in mind the output needs to be evaluated at the original output also. So this is g, not g of q, but g of f of q. So whatever the original output is, and shows up as a transpose on the left, which is kind of a normal way this kind of stuff works. So that's right. So I just g's on both sides here. This thing in the brackets, the whole thing is what we're going to call del F here. And this guy is going to be, in the case of quaternion to quaternion, this is going to be a 3x3 thing, because I'm transforming it to map from perturbation on the input, perturbation on the output. And the idea here is it's basically transforming the input on the right and then transforming the output on the left. Cool. Okay. So then like kind of the last one we need is the Hessian of a like scalar value thing, which is Hessian of a cost function is where this comes up, right? So this guy, so it's similar, it's a scalar valued function. So if each quaternion spits out a scalar, it's a cost function-y thing. And this we're just going to write as del squared of f. And it's pretty much what you expect. It's going to do remember the Hessian is something that I want to sandwich by delta x's on both sides, the quadratic form. So I've got to transform both inputs from both sides. So I pick up g's on both sides of this guy. But it turns out I also pick up an extra term on here that's coming from dg dq, which shows up when if I take this thing and take a second derivative, I get like a chain rule situation. So I pick up another term. Another way of thinking about this is like the full Newton Hessian, and that's like the Gauss-Newton thing. Like there's an extra second, there's a curvature term here that comes out too. And this looks like this. So this is, 3x3 identity. And then this is, this whole thing's a scalar. And this term is coming from this like partial G, partial Q, this like next derivative of that attitude Jacobian thing. Okay, that's all the things you need. So now you know how to do gradients, Jacobians, and Hessians. You have all the ingredients for like applying this to all of the stuff we've done so far. So you can do like Newton's method, you can do LQR, you can do DDP, like all the stuff. And you just bolt this G matrix on wherever you need. Anywhere a quaternion shows up on the input or output of the function, take the Jacobians or take the Hessians like normal, and just stick the G's in the right spots. Okay, so that's the message. Now, and do Newton's method and EDP and SQP, all the things. Okay, any questions about this so far? So now we're going to do this on a real problem, and I'll give you some code. So we're going to do an example that's, I don't know, the simplest example that does this stuff that I could think of. So we're not going to go do a full up triage out problem. We're going to instead do a problem called Wahba's problem. Has anyone heard of this before? This is pose estimation just for the attitude though, not the position. So the idea is assume you've got, so let me write this down. So this is a very classical like aerospace problem. So it's just attitude estimation, I should say, not pose estimation. We're not doing the position part. So the idea is you have a camera in your, or whatever, like we can abstract this a little bit. The idea is the way to think about it is I have a camera in the body frame, like on the robot or on the spacecraft, which is classically where this comes from. And I'm observing a bunch of vectors to known features in the environment, known landmarks, say, in my camera. So let's just forget camera details right now and just assume. So with the camera, I can observe, like assume I've calibrated my camera. So I know what the body frame stuff is. So let's say I observe, like, I don't know, the vector to that clock, the vector to that exit sign, whatever in my camera. And so I know what those vectors are in the body frame. And for this, I just need unit vectors. So I need to know the unit vector directions to those things in my body frame. If I have a map of the world, I know where those things are in the world frame already from the map. Now I have pairs of vectors. So I have the vectors I observe in the camera frame. And then I have the vectors I know from the map, right? Make sense? So then I have these pairs of vectors, and I'm now going to basically set up and solve a least squares problem for the attitude, given a bunch of these vector pairs. So that is Wahba's problem. And I'll write down the math for it right now. Given a bunch of vectors to known landmarks in the environment, determine the robot's attitude. Yeah, so the classic, where this comes from, this has an interesting history also. This problem was like originally comes from the early 60s, like the birth of the space program and stuff. And it was originally posed as a challenge in like a journal. It was like posed as an open challenge. And the name Wahba is from Grace Wahba, who's a statistician at, I think, University of Wisconsin. She only retired like 10 years. I think she's still alive. She retired like 10-ish years ago. But this was like a completely it's like it is known as Wahba's problem, like it is associated with her. And it was this most random aside that she didn't care about at all. Like it was this random thing that she did like as a grad student or something. And like she went on to have a long career in statistics and like didn't never care about this. And she became like famous in the aerospace community and like has this thing named after her. Kind of funny. So let's see. Okay, so here it is written out in math. It's a least squares problem for the like attitude, the Q, and it has this kind of cost that we're going to minimize, which is a least squares, loss. So let's say we have m of these vectors, and this is what the least squares cost looks like. It's so I have this unit vector, um, unit vector k in the n frame, so like the inertial world frame, whatever you want to call it, and then I have the same vector observed from my camera in the body frame. And I just take the least squares loss over all these vectors. So observe it. So to be super clear, right, this is assuming I know my location already. I'm just solving for the attitude. So if I have a map of the room and I know where I'm standing in the map, and I know like all these features, I say, okay, I see that thing in my camera. I know where I am. So I know what this vector is in the inertial frame. I know what it is in the camera frame. I have a few of those. And then clear to everybody? That's the setup. Okay, and so this, we can like sort of abstract this slightly into just like a classic thing in least squares is to define a residual function. This residual function. So this is a big vector that's just all the errors. Right. So here it's if I put this is up for each pair of vectors, which is just one giant vector. We're going to call that the residual R. And then so it's that thing, the sum of the squares of the residuals, aka R transpose R, right, is the thing we're minimizing. Okay, so let's see. Let's write some notes on here. So this is known vectors in world frame, aka from the map. This is observed vectors in the body frame from the camera. And then this R thing is the residual vector. Cool. Has everyone heard of this before? Residual least squares, hopefully a little bit. Okay, so this is a pretty classic nonlinear least squares problem with just the one twist that the thing we're solving for isn't a vector. Rotation vector. So there's just a little extra twist on the classic least squares setup. Okay, let's see. So let's write this thing down in a little more detail, the residual thing. And remember, so x, these x's and are unit vectors. We don't care about their magnitude. We're just trying to estimate attitude. So directions is the way to think about them. And this residual function looks like just I'm stacking up all the individual observations. So it's there's the first feature vector that I observe, the second one, dot 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 until the mth one. So that's all the x's, and like it's the same q, right? Okay, so this is my residual vector, and the way we're going to do this, obviously we need like try to minimize the thing Gauss-Newton, standard thing to do in least squares. So to get there, we need the Jacobian of the residual vector. So let's do that. So we want this, what we're going to call del r, and this guy is going to be let's write it down. So we're gonna do the stuff we just said. So we're gonna diff it with respect to q as if q were just a vector, and then we're gonna tack on this Jacobian guy. And just to clarify some stuff, this guy, we want this to be 3m by 3. This thing is going to be 3m by 4. And this guy is going to be 4 by 3. That's how the dimensions work out. Right. So we have m observations. Get the idea. Okay, so just as an aside, we've kind of touched on this, but to make sure we're super solid on this, we're gonna just recap Gauss-Newton for least squares. So the least squares problem, you can like sum it up as min. Oh man, I went RL there for a second. All right, so like generic least squares, it's min over some x of some cost function, which is like the minimizing the 2 norm of this residual vector squared, which is where the least squares comes from, which is equivalent to R transpose R. Cool. So the way you solve this is you take partial of your loss function with respect to x, aka the gradient of this loss function, which for least squares, this has a very particular form. So if I take this guy, I'm just gonna do my usual chain rule stuff. That's R transpose dr dx. And then, so that's the gradient. I'm gonna write down the Hessian next. That looks like e squared j dx squared. And if I just kind of like, I'm gonna get partial r partial x transpose partial r partial x. That's, just me taking this. So if I do that using all that cron-vex stuff that we talked about before, that turns out to be I cron r, I suppose, times d squared. So that's like the stuff we talked about last time, right? Okay, so remember we talked about this with DDP versus ILQR, Gauss-Newton. If I were to use this whole section, a Newton method, but this is annoying. I don't like this, so I'm just going to throw this out and just keep this. That's called the Gauss-Newton method. So we're going to throw this guy out. By the way, this is like the original context where Gauss-Newton comes from. It's a statistics least squares fitting thing, classically. Okay, so that's the whole thing. And I get the following like kind of Newton step thing. I'm going to approximate that with this Gauss-Newton stuff. So it's going to be dr dx transpose dr x inverse times dr dx transpose times r of x. Okay, that's the whole thing. So this is our Jacobian of our residual function. There's our residual function. This also looks like very, very similar to the normal equation for linear least squares, right? If it were a linear least squares problem. Cool. Questions about that? Hopefully you've seen this before someplace. Everyone good? That's classic Gauss-Newton. It looks like Newton's method stuff that we've been doing. Okay, so now we're going to do it for Wahba's problem with the quaternion tricks. It's literally just going to be this, but we're going to swap the x for a q and plug in our attitude Jacobian business. Okay. And I think this basically sums up all of the weird things there are to know about optimizing over rotations in like the simplest, setting possible, I think. And then from here, you can go do it on all the stuff we've been doing. / you will on your homework also. So, okay, so we're going to initialize this with some guess Q naught. And I'll like write out the full pseudocode. And then we're going to do the following stuff. All right, so we're going to compute our gradient. Which, to be clear, is this thing. I already wrote down. Then we're gonna take our Gauss-Newton step. Or sorry, that's Jacobian of residual. Then we're gonna compute our step, which is gonna be one of these little axis angle guys. And it's gonna be this kind of deal. Cool. That's our little 3-parameter thing. And then we're gonna update Q with a multiplicative update. And the way we're gonna do that is we're gonna multiply it on from the right, like with all the tricks that we've been playing. So it's gonna be Q times, or maybe I'll use the L of Q thing. All right, well, I'll write it both ways here. So it's Q times, we're going to take that phi and turn it into a unit quaternion. And we're going to use kind of the vector part of the quaternion kind of parameterization when we do this, which is equal to L of Q times this guy. And the key thing is, right, it's a multiplicative update. The reason we do this is if I do it right, this guy's a unit quaternion when I start. This is always guaranteed to be a unit quaternion by construction. So like this multiplication, always guaranteed to be a unit quaternion by construction. So lots of fancy math ways of talking about this, but the gist is this algorithm always guarantees that every iterate is a unit quaternion. So another way of saying this is I stay on manifold, like I'm always staying on the unit sphere. I never have to worry about extra constraints. I never have to worry about the uniform constraint. It just does it. It's all kind of built in, right? All right. Cool. And then in general, you would also do a line search on this. You'd use your Armijo stuff, like the usual stuff. But it turns out this problem's like benign enough that we don't really need one. So I'm not going to do it here, but it's super straightforward to do those standards that we've been doing. And then, this whole thing, kind of until your convergence criteria is satisfied. In this case, it's going to be like norm of the residual bigger than some tolerance or something like that, whatever. Okay. Questions about this? It's a classic Gauss-Newton. The only difference, literally, this could have been the original Gauss-Newton algorithm, like with the 2 exceptions of slap on this attitude Jacobian here. And then when I apply the update, if this were normal vector land, I would get from delta x, and I'd do, I'd add it on. But instead, I'm going to take this 3 parameter guy, I'm going to turn it into a unit quaternion, I'm going to multiply it on. Cool? Everyone good with that? Okay, code. I swear this stuff's cool. You can actually this is how you make backflips happen and stuff. So we'll do that. You do that on the homework and stuff. Flash maybe a little bit next time. Cool. So this is all the random functions we derived like before. You got your map cross producty thing. You got your L matrices, the E and H stuff. This is all just stuff to have. Attitude Jacobian, rotation matrix as a function of Q. The way I'm going to do this, I'm going to generate a random quaternion. So the simple way to do that is to generate a random 4 vector and then normalize it. It turns out that's actually a good way to generate uniformly distributed quaternions, since it's actually statistically legit. And then we're going to generate a bunch of random vectors, normalize them so they're unit vectors, and then rotate them to generate our observations. Just arbitrary, I'm going to generate 10 vectors here. Cool. Here's my residual. This exactly we just wrote down. It's the inertial frame one minus the body frame one rotated by our Q. Return that whole thing stacked up. I'm going to make a random initial guess. Again, just generate another random unit quaternion. Then here's my Gauss-Newton method. So by the way, another good reason for this whole attitude Jacobian thing is that it plays nice with auto diffing, right? So I can so what I'm doing in here, right? So here's the algorithm, make a random guess. I compute my residual. And then to get my Jacobian, I just diff the residual function as if Q is a normal vector. So I can just use 4diff on this, get the Jacobian. Then after I do 4diff, I just slap on the attitude Jacobian. There's my Jacobian I actually want to use. Here's my Gauss-Newton step. And then I take this guy, I turn it back into a unit quaternion here and multiply it on. And then I'm just going to loop this until, the residual is small. Boom. 6 iterations. Okay, here's a fun one. Check this out. This is huge error. What about this one? Yeah, look at that. It's exactly right. So what happened there? If I do this, yeah, exactly. Yeah. So this is, remember, we're doing Newton. It's going to converge to whatever, is closest to the initial guess. And since we have Q and minus Q correspond to the same rotation, it literally just depends what my initial guess was. If I'm closer to this one, I'll go here. If I'm closer to this one, I'll go here. They're equivalent. They get you. So if I were to repeat this a handful more times with different random guesses, I'll get it to go both ways in general. Yeah. So this time it went the other way. So that's kind of interesting. In practice, there are some annoying things there with the double cover stuff. Namely, what can happen is this is all stuff that you need to just be aware of and be careful about. We'll talk about this a little bit next time. If you're doing a controller that's trying to track a desired attitude, you have to be a little careful about this, because if you're naive about writing your cost function down or whatever, and you're trying to track a particular Q, you can have a situation where your state estimator spits out minus Q, and then your controller freaks out and tries to literally wrap you around by 2 pi. This has a name in the control lingo. It's called the unwinding problem. So if you're not careful, you can have a controller that thinks you have a 2 pi error and tries to flip you around when your error is actually 0 effectively. But you just have to be a little careful, and then it's not a problem. Cool. Anybody have questions about this?